4.6 is on volumes of solids with cross sections. We're going to talk about the disk method and the washer method as well. So one thing I want to preface this section with is that a lot of what we're talking about, you really need to have a visual understanding of what's going on. And with my technology limitations for making these videos, I really can't show you those during this particular video. I am going to show you some great visuals to help you understand what's going on when I teach this lesson live, and there are links to those visuals in the slideshow. So if you're watching this video and you're trying to visualize what's happening, know that there are other resources out there for you to see that, because I can only do so much with what we have here. So let's say that we know the base of a solid of the graph is y equals negative x squared plus 4, and we're looking at the region between the two axes, so the shaded region in this graph below. So think three-dimensionally. This is a shape that is being made up of. So if we know the solid is being made up of square cross sections that are perpendicular to the x-axis. So again, I have no three-dimensional drawing skills here, but if think about right here, this is a square that is coming up three-dimensionally. There's another square coming up three-dimensionally. So they're coming up vertically off the graph, and they are squares. So it's like you're thinking about an infinite number of squares along this part of the curve that are creating a volume. And since it is a square, the height and the base are going to be the same length. So each side of this square is going to have length negative x squared plus 4. Which means that each square has an area of negative x squared plus 4 squared. And then the thickness of each square is the change in x, which means that the thickness of each square is really dx. So each square has an area of negative x squared plus 4 quantity squared and a thickness of dx. So thinking back sort of to the idea of a Riemann sum, if we're adding all of these areas together as they're going over and forming this curve, that would be the idea of integration here. So we can add up the area of all of the squares and of the square prisms using integration to find the volume. So we could say that the volume is equal to the integral from some a to b value of the area being integrated with respect to x. So the area sort of times the thickness. Or in this case, for this particular problem, the integral from a to b of negative x squared plus 4 squared dx. So the idea here, and I'm going to give you again in class some better visuals, is that we're finding the area of each of those squares and we're integrating it with respect to x. That's going to give us this overall sort of volume of the region that we're looking at. So squares going up off of this area here. So for these notes, I'm really going to focus on, in this video, showing you the math portion behind it. I'm not going to focus quite as much on the visual just because of the three-dimensional limitations that I have with what we're looking at. So for problem 1, it says we're going to be finding the volume that is bound by negative x squared plus 2 and y equals x. And it's specifically telling us that the cross sections, meaning the vertical prisms that we're looking at here, are going to be rectangles that have a height of 0.25 inches, and they are perpendicular to the x-axis. And when you hear things like perpendicular to the x-axis, that is telling us that we are going to differentiate with respect to x, because this is changing in terms of x. And you will see problems today where this volume formula is actually the integral from a to b of the area with respect to y if the curve that we're talking about is in terms of y. So that's not true on this particular problem. We're talking about cross sections that are perpendicular to the x-axis, but if they were perpendicular to the y-axis, we'd be integrating with respect to y. So let's think about what just one of these rectangles looks like. So right here would be a rectangle. Think about it coming out of the screen towards you three-dimensionally. It has a 1/4 height, and it has negative x squared plus 2 minus x, because we are subtracting these two curves. That's going to give us the dimensions of this rectangle. So we're looking at only this area between these two curves, and we're looking at a rectangle that's being formed here, a bunch of them that are coming up vertically and creating a volume for this entire piece of the curve. So they're coming up towards you out of this curve, sort of like a little hill. So the volume is going to be the integration of the area. So what's the area? Well, the area here would be 1/4 times negative x squared plus 2 minus x. That means that the volume, and I'm going to pull the 1/4 out since it's just a scalar. The volume is going to be the integral, and let's look at the intersection points here. The integral from -2 to 1 of this curve, negative x squared plus 2 minus x, integrating with respect to x. Now, this one is pretty simple. There's no calculator symbol to do by hand. This would be negative x to the third over 3 plus 2x minus x squared over 2, being evaluated from -2 to 1. And for time's sake, I'm just going to tell you that this simplifies to be 9/8. So when you're doing these problems, really focus on trying to get a visual understanding of what's going on. Like, what does each individual cross-section shape look like? What are the dimensions of that cross-section shape, so that you can identify the area. Then you're going to find the volume by integrating the area. So let's look at number 2. The directions on number 2 say set up the integrals to solve the following, given the circle x squared plus y squared equals 1, and cross-sections of, for part A, we're looking at equilateral triangles that are perpendicular to the y-axis, which means we are going to be integrating with respect to y. That also means that our equation needs to be in terms of only y, which means we're going to need to manipulate this equation to solve for x. But let's first graph and get a visual idea of what's going on here. All right, so I have this circle and I have an equilateral triangle, meaning all the sides are the same. And I want you to think about for a minute, what is the length? What is this length, the length of each side? Well, if we solved this equation in red for x, we would get that x equals the square root of 1 minus y squared. So that would be this length right here, which means that whole length, one side of the equilateral triangle, one side would be 2 of those. 2 times 1 minus the square root of y squared, if I solve that equation for x. That's what each length would be. So what we need to do is we need to integrate the area of this triangle. Well, in case you have forgotten, the area of an equilateral triangle is root 3 over 4 times one side length squared. If you didn't know that, it's pretty easy to derive. It comes from special right triangles. But for time's sake, I'm not going to derive that for you. And we just said that each side has length 2 times 1 minus the square root of y squared. So the area would be equal to root 3 over 4 times 2 times the square root of 1 minus y squared squared. Which is going to mean that this 2 is going to become 4 when I square it, which means the 4 in the denominator is going to go away. So this area is going to be root 3 times 1 minus y squared. I'm going to take up a little space down here. So to find the volume, which is what we're being asked, that's going to be root 3 times the integral. And let's look at our y values here. We're going from -1 to 1 of the area, root 3. Oops, I already put root 3 out front. 1 minus y squared dy. This is another one that's really easy to integrate by hand. We're just being asked to set up. So here is the set up integral that would give you the volume of these cross sections. Part B is asking us to do the same thing, except now the cross sections are going to be rectangles whose heights are 3 times their bases and perpendicular to the x-axis, which means now we're going to be looking at dx instead of dy. So now we're forming our rectangles this way, and that length in terms of x, so each base is going to be equal to 2 times, now in terms of x, 1 minus the square root of x squared. The height is going to be 3 times that, so that's going to be 6 times 1 minus the square root of x squared. So the area of one rectangle is base times height, which is going to give us 12 times 1 minus x squared, which means our volume is going to be the integral of 12 times the integral from -1 to 1 of 1 minus x squared dx. So again, the process that you're thinking through for these cross-section problems is draw a picture so you can identify the shape, find the area of the shape, integrate the area of that shape in order to find the volume. The next thing we're going to talk about is the disk method. So here we were just finding on these first examples the area or the volume based on cross-sections being formed. If you can picture the x or y axis as an axle where we are rotating a shape through space to get a three-dimensional solid, what happens when we do that is that the lines that we are rotating become circles. So I know this is going to be hard to visualize without me. Usually I would use my arm to show you this. You can't see my arm. And we are going to see a visual in class. But think about this. You have part of a curve, and you're rotating that curve around a line, and that's creating circles. That's creating a figure. And because that creates circles, that's why we call this the disk method, because disks are circular. Our function is now going to be in terms of the radius. Our actual function is creating the radius of a circle as it's rotating around whatever axis we're rotating about, which means that our area when we use this method, when we're rotating, is going to be pi times the radius squared, or pi times the function squared, which means, based on what we just did, our volume is going to be integrating that area. So I'm going to just take pi out. The volume is going to be the integral of the radius, pi times the radius, pi times the integral of the radius squared dx, or dy, again, depending on how we're rotating. So what we're doing is we're integrating each of the disks, and make sure that you're always using radians. Let's look through some examples. I think this is going to help you understand what's going on here. So determine the volume of a solid formed by rotating the region bound by y equals x squared, y equals 0, and x equals 1. And we're going to be rotating around the x-axis, which means we're also going to be integrating with respect to x. Let me draw a picture of what we're saying here. So here's our curve. It's being bounded here. But what we're doing is we're taking it and we're rotating it around the x-axis. So it's creating sort of this cone-like, if you were to look at it three-dimensionally. But each thing that we're finding the area of is an individual circle, and that's why we're talking about using the radius here. So each rectangle rotates and creates a circle. So when we're finding the volume, what we're doing is we're saying pi times the radius squared, and the radius is the function. The radius is the function. So the volume is going to be pi times the integral. We're going from 0 to 1 of the radius, aka the function, squared with respect to x. So pi times pi r squared, and we're integrating that area. Well, this would just be pi times x to the 5th over 5, being evaluated from 0 to 1, which is just going to be pi over 5, or 0.628. Sketch each situation, set up the integral, and find the volume. You may evaluate the integral using a calculator, but it's probably good for some of these, at least for number 4 maybe, to practice evaluating by hand. So go ahead, start by sketching a picture for both 4 and 5, and seeing if you can set up that integral. So for number 4, we have a piece of a quadratic here. So we're looking at this. This is being rotated around the x-axis, which means it's coming around and around this way. So it's creating a circle which with each individual part of the function that's rotating around the axes. So again, the volume is just going to be pi times the integral, and here we're going from 0 to 1, of the radius, which is just the function, squared, being differentiated with respect to x. This is one that would be really simple to do by hand. You would need to square this polynomial out and then actually use the power rule to integrate, but I'm just going to, for time's sake, tell you that this is equal to 0.105. Units would be cubed if we were given specific units on this problem. Looking at number 5, we're looking at the region bounded by y equals the square root of sine of x and y equals 0 between 0 and pi. So they're telling us our bounds here. They're telling us we're going to integrate with respect to x since we're rotating around the x-axis. The area that we're talking about would be pi times the square root of sine of x squared. So that means that the volume would be pi times the integral from 0 to pi of sine of x dx. This you could very easily integrate. This would give you negative pi times cosine of x evaluated from 0 to pi, which is going to give you negative 2 pi. Now the disk method, if we were rotating around the y-axis, if the function is being rotated around the y-axis or any vertical line for that matter, we need to make sure that our function is in terms of y so that the height of our rectangles is also in terms of y because we're going to be rotating around the y-axis or around a line parallel to the y-axis. So let's look at a couple of examples here. Find the volume of the solid generated by rotating the region bound by x equals y to the 3 over 2, x equals 0, y equals 0, y equals 3, about the y-axis. So first, draw a picture of what's going on, find your area, and then to find the volume, integrate that area, this time with respect to y, since we are talking about the y-axis. So here's a very rough sketch of this curve. We are rotating this curve around the y-axis, so again, it's sort of making a cone-like shape, but the things that we're looking at to find the volume are going to be those circles. We're adding up the area of all of those circles in order to find the volume. So let's talk about that area. The area is going to be pi times the radius, which is y to the power of 3 over 2 squared, which that simplifies pretty nicely. That's going to give me pi times y to the third. So our volume is going to be pi times the integral from 0 to 3, because look at the y values we're integrating from 0 to 3 of y to the third dy, which is obviously going to be pi times y to the fourth over 4, evaluated from 0 to 3, which is going to be 81 pi over 4 for our area. Why don't you go ahead and try number 6 on your own? So here is an image of what's going on. We're rotating that shaded region around the axes, and this should have, I apologize, a calculator on it because we do not know how to integrate something like 2 to the power of y. So our area is going to be equal to pi times r squared. So pi times 2 to the power of y squared, which is pi times 2 to the power of 2y, which means our volume is going to be pi times the integral, let's look at our y values, from negative 1 to 4 of 2 to the power of 2y dy, and this you would need to do on a calculator. We have not talked about how to do this by hand. This is going to be 579.576, and again, if we were given units, this is volume, so they would be cubed. So we have talked about cross sections, and we have talked about the disk method. Now we're going to tie 4.6 back to 4.5 where we're talking about the area between two curves, and that's going to lead us to the washer method. So in case you're not handy with tools and things, a washer is a piece of metal that is made up with it looks like a disc, but it has a giant hole in the middle of it. Just like a CD, a DVD, or a Blu-ray, those could all be other names for this method, although I think some of those things are even more outdated than thinking about a washer. But what I want you to think is, if we have a curve like in this picture, and I'm rotating this curve around the x-axis, unlike what we just did with the disk method, this piece is rotating. When that rotates, there's going to be a hole in the middle of the disk. When this goes around and around and around, there's a gap in here where there is no area. Again, I'm going to show you a better visual in class. But because of that, we need to think about the two areas that we're integrating. We need to think about both areas separately in order to perform this integration. So this is a lot like what we just did, but now we're talking about two different curves, and that's going to come into our formula and the idea of the washer method. So let's pretend we're standing on the x-axis, maybe around like x equals 4, and we're looking to the left. We're going to see something like this green curve here. We're going to see a circle, well, three-dimensionally, so I guess pieces of spheres, but there's a giant hole in the middle, and for this particular curve, that hole is x to the 4th, because the blue line is 8x, and the curve underneath it is x to the 4th, so when that rotates about, the inside hole is x to the 4th. So when you are doing this volume, you're now going to have two radii. The big function radii, which we're going to use capital R to represent. In this case, that capital R would be 8x. And the smaller radius, which is the second function, the lower function, again, this is like big, small, thinking through from 4.5, would be x to the 4th. So the area now is going to be a little bit more complicated. It's still pi times r squared, but what that means is I'm going to be taking 8x squared minus x to the 4th squared, the big squared minus the little squared. That's going to give us our area. So if we're talking volume, the process is the same, pi times the integral of the area squared. So this looks like in terms of x, it's going from 0 to 2 of this area, 8x quantity squared minus x to the 4th quantity squared, all being integrated with respect to x. And I'm just going to tell you that this ends up being 357.443. So our job when we're doing these problems is to figure out which is our big radius, which is our small radius, our big and little functions, just like in 4.5. The curve from the axis of rotation will give us the big and the small. So looking at and thinking about how we're rotating, which is bigger, which is above, and our integrand is always going to be pi times big radius squared minus little radius squared. All right, let's look at some more examples. Determine big R and little r. We're not even going to do all the integration, although I might set up the integral anyways, but the big thing first is that you can identify which is big R and which is little r. So I drew very rough sketches here for 1, 2, and 3. So we're looking at y equals x squared and y equals x. We're rotating it about the x-axis. So we're looking at which is further away, which is big in this case. Well, y equals x is on top. So big R is going to be basically the function x, y equals x. Since we're rotating about the x-axis, this means we're going to be integrating with respect to x. So we want to leave it as x. That means that little r is our quadratic, which is x squared. So if I was to set up this integral, I would say that the volume is pi times, this goes from 0 to 1, of x squared minus, I should say x squared squared, minus x squared with respect to x. On number 2, since we're rotating around the y-axis, that means we're going to be integrating with respect to y, which means we are going to solve this to get x equals square root y. Big R, further from the y-axis, is going to be that square root y. Little r is going to be just y. So we could set that up as the pi times the integral from 0 to 1 of square root y minus y squared dy. For number 3, the thing to keep in mind is that we are rotating around the axes y equals 5, which is parallel to the y-axis, which means we're going to be integrating with respect to y. The other thing to keep in mind is that since I am 5 away from the function, I actually need to define my functions by 5 minus what was there before. So big R is going to be 5 minus the square root of y. Little r is going to be 5 minus y. And I could set up that integral as pi times the integral from 0 to 1 of big R squared minus little r squared. You can go ahead and pause the video and work through 4 through 7, but there are a lot of examples here. So what I'm going to do is just talk through the key points and you can see the work there as it is with the sketches and how I defined things. So the key thing on number 4, since we are going to be rotating around the y-axis, the functions need to be in terms of y, and we need to be integrating that volume with respect to y. On number 5, everything is pretty basic. We're rotating around the x-axis, so we're going to be differentiating, or we're going to be integrating with respect to x. I think that one is pretty straightforward when you're looking at big R versus little r. 6 and 7 are a little bit more complicated because we are not rotating around the x or the y axis. We are rotating around a line. So x equals 5 is a vertical line, which means we are going to be integrating with respect to y, which means not only do we need to convert our functions to be in terms of y, so the square root of y equals x and y equals 2, we also need to do 5 minus those functions because there is a big gap between the line x equals 5 and both of the functions. So big R is going to be 5 minus root y, little r is going to be 5 minus 2 or 3. And then you can set up your volume integral with respect to y. 7 is even weirder because we're rotating, we're going to be integrating with respect to x, but y equals -1 is below the axes. So think about that. You're not just, think about the distance. You're 1 away from the axes and then you are away from the curve. So what you can say is the curve minus -1 or 1 plus the curve because you're adding that distance away. There should be a dy after that volume or a dx after that volume integral, which is missing as well. So pause the video, work through those problems, and then check your answers. And we're going to do the same thing for the rest of the problems in these notes. So the thing I want you to be thinking about once you start working on 8 through 11 is that not every problem is, well, most problems aren't going to tell you use the washer method or use the disk method. You really need to sketch your function and see what is happening. Are we talking about a curve that when I rotate it is going to have a gap? That means I should use the washer method. Are we talking about something that's not going to have a gap? That means I can use the disk method. You're going to be using cross sections when the problem specifically tells you use cross sections. So something to notice on 8, there is no gap. There is no hole when we rotate that. So you can just use the disk method. For 9, there will be, and you're going to be rotating around the y equals -3, which means you need to add 3 to each of your functions to accommodate for that distance below the axes. So pause the video, work through 8 and 9, and then unpause and we'll talk through the interesting parts of 10 and 11. Note that all of these are calculator problems it said at the very beginning, and you have no idea how to integrate with natural logs, so definitely going to need to use a calculator here. For problem number 10, just remember that since you're rotating around y equals 2, you're going to be integrating with respect to x, and that you need to do 2 minus each of those functions when you are setting up your big R and your little r. And last but not least, on number 11, you're rotating around y equals -1, so you need to add 1 to each of your functions. And you would be using a calculator on both of these problems to find the intersections for the bounds of that integral. So key things for the lesson today: when you are working with cross sections, make sure you're finding that individual area of one shape and then integrating that area. When you're using the disk method, the function becomes the radius and your volume is going to be pi times the integral of the radius squared dx. When you are using the washer method, you're considering the hole in the functions when they are rotating about that axis, and that's why you have to identify big R and little r and square them. So your volume will be pi times the integral of big R squared minus little r squared with respect to the function that we are looking at. We will be doing more practice on these in class. There are great resources in Google Classroom as well, and I look forward to supporting you with 4.6. See you in class. Thanks for listening.